Hello everyone, and welcome to my channel, Square Wave 2. Today I'd like to talk about the physics of the violin. The violin is a member of the stringed instrument family, consisting of the violin, the viola, the cello, and the double bass. All four of these instruments operate on exactly the same physical principles. They use the same parts, and they're made in much the same way. They all begin with a tailpiece down here, with strings attached that are stretched over a bridge up here to the peg box. Each string has its individual peg. This is for adjustment or for tuning the instrument. Now, the violin has four strings, G, D, A, and E. Now, if I crank the peg on the D string to increase the tension, the pitch will go up and the string will vibrate at a higher frequency. If I decrease the tension on the D string, it will vibrate slower at a lower frequency. The violinist will first tune his A string, and to do this he needs some kind of a pitch standard, either a piano or perhaps a tuning fork. Here's a tuning fork. This instrument has been scientifically designed to vibrate at exactly 440 cycles per second. This is the internationally agreed upon frequency for A above middle C. To activate the tuning fork, I tap it against something firmly like this. And then I place it against the body of the violin to amplify the sound. And with this pitch, the violinist can adjust his A string so it matches the tuning fork. And by the way, don't confuse a tuning fork with a pitchfork. A pitchfork is for pitching hay, and a tuning fork is for making a pitch, if you can understand that. Now, after the A is tuned, the violinist has to tune his D, G, and E strings, and he does this by playing two neighboring strings together. To tune the D string, he'll play D and A together. A is already tuned, and he'll be listening for something called a perfect fifth. That is the interval of 5 notes. For example, here are the D and A strings together. I'm going to adjust the D string until I hear a perfect fifth. And there's the perfect fifth, so I know my D is in tune. Now, to adjust the G string, I'll compare it to the D string with the bow, again listening for a perfect fifth. And the E string is played with the A string, again listening for a perfect fifth. All the stringed instruments are played with bows that are strung with real white horsehair. The horsehair has microscopic barbs that pluck the string continuously as we draw the bow across the string. And to increase this action, we apply something called rosin. Rosin is actually made from the sap of a tree, and it increases the action of the horsehair on the strings. In order to play a tune or a piece of music, we're going to have a way to adjust the pitch on each string very rapidly and very accurately. And cranking a peg up and down is not going to allow us to play a melody. What we do is shorten or lengthen the amount of string allowed to vibrate. The shorter the string, the faster the vibration, the higher the pitch. The longer the string, the more slowly it vibrates, and the lower the pitch. Here's how this is accomplished. When playing a piece of music, a string is effectively shortened by holding it down against the fingerboard with your finger. Now the portion of the string allowed to vibrate is from the finger to the bridge. The portion of the string between the finger and the peg box is totally inactive. By the way, this note is called open A because no finger is involved. It's the lowest pitch on the A string. Now if I move the finger up towards the bridge, the string vibrates faster and faster because it's shorter and shorter, and the pitch gets higher and higher. Now if I put the fingers down consecutively in order, I can play a scale. And if I raise the fingers in order, I can play a descending scale, ending with no fingers, open D. There's a lot more to music than just pitch and melody. There's something called dynamics. How loudly or how soft are we going to play? Are we going to gradually increase our volume in certain places and gradually decrease it in other places? These are a matter of dynamics. On a violin, in fact on any stringed instrument, if I want to play loudly, I use a heavy bow pressure and a fast bow speed, like this. And if I wanted to play the same thing very softly, I'd use a very light bow pressure and a slow bow speed. And that's what we call dynamics. All the stringed instruments, violin, viola, cello, and double bass, use something called vibrato to warm up their sound. This is a rapid variation in pitch done by rocking the finger back and forth on the string. Here's a close-up of the vibrato motion. The finger is rocking up and down on the string. What we are doing is alternately shortening and lengthening the amount of string allowed to vibrate, thereby creating a slight variation in pitch up and down. For example, here are a few notes without vibrato. Kind of plain, kind of austere, not too pleasant to listen to. Now the same notes by using vibrato. Quite a difference, a much warmer sound, much more like the human voice. Now we come to the fascinating subject of harmonics. Harmonics are a whole number of multiples of a fundamental frequency. For instance, the fundamental frequency times 2, times 3, times 4, times 5, etc., etc. It is the harmonic series that give each instrument its distinctive sound, or timbre. For instance, you couldn't possibly confuse a violin with an oboe when they're both playing the same 440 cycle A. You couldn't confuse a violin with any other instrument playing the same note at 440 cycles per second. I have my audio generator set up to produce a sine wave at exactly 440 cycles per second. Let's take a look at it. Well, pretty boring. Just a simple sine wave, no harmonics. Now let's look at the violin playing exactly the same fundamental note at 440 cycles per second. And I think you'll see a drastic difference. Well, that was pretty exciting. There's certainly a lot going on. The scope tries hard, but it can't possibly keep up with all the harmonic structures above the fundamental frequency. But it's amazing to see how fast an electron beam can be moved about within a cathode ray tube. Of course, there's a lot more to the physics of the violin than just the action of the strings. The wooden body acts as an acoustical amplifier, and the quality of sound coming out of this amplifier depends upon many things. What woods were used? How were the woods aged? What was the skill and dedication of the builder? What varnish was used? And very important, is the violin completely played in? Yes, generally speaking, the older the violin, the better it will sound. The finest violins were made between the 17th and 18th centuries by men like Amati, Stradivari, and Guarneri. These instruments are worth millions and millions of dollars, and they don't change hands very often. They're all well cataloged. The violin is a difficult instrument to construct. It's very hard to make. It takes years of practice and training to create an instrument. Also, the violin is a very hard instrument to play. I'm sure you've noticed there are no frets like the guitar has. There's nothing to tell the violinist where the fingers go except his ear. And once he learns where the fingers go, he has to remember the relationships. Well, I'm going to sign off today with a very well-known and well-loved melody.